Before we start solving this question, I recommend that you go through the handout that I uploaded on Google Drive related to memory management technique. Okay, so let's start solving this question. Okay, this question is related to paging, right? And this is the page table which shows this is the page table related to one process called X. Remember, there can be many processes running in the computer at the same time, but this page table is for a single process called X. Okay, let's take a look at the page table, and this page table shows that we have a total of 135 pages in the process, right? This is the maximum number of pages, and some of the pages are present in the RAM. For example, page number 1 is present in the RAM because the presence flag is 1, but page number 4 is not present in the RAM right now. Okay, so the presence flag is telling us which page is present in the RAM and which page is not present in the RAM, and the page frame address is telling us the location of page number 1 in the RAM. And so page number 1 is located at page frame 132 in the RAM. Page number 5, for example, is located at page frame number 542 in the RAM. Okay, let's move forward. What we can also see is that the additional data field has not been, there are no values here, which basically means somewhere down the line this question is going to ask us to fill this field, right? So we're going to take a look at the question and see what he wants from us as far as additional data is concerned. Okay, next he is saying that the page frame address for page 2 is 245, and he's saying, what does that mean? Basically, what that means is, we break RAM up into equal sized parts which are called page frames, right? These are called page frames. So this may be page frame number 1, and somewhere here, this might be page frame number 245, right? So what does the value 245 represent? What it basically represents is, starting from the top of the RAM, this is page number 1. So page number 245 means what? The 245th page frame from the start of the RAM. So this would be page frame number 1, and 245 represents what? The 245th page from the start of the RAM. Okay, so this value 245 represents the 245th page. I should not be saying the 245th page, I should be saying the 245th page frame, right? These are page frames, right, in the RAM. So the 245th page frame from the start of the RAM. Okay, then he says that the process keeps executing, which means instructions within the process keep getting executed until we require an instruction which is lying in page 4, but page 4 is not inside the RAM right now. Which means what? Where would page frame 4 be? If you've studied the concept of virtual memory, if a page is not present in the RAM, then that page is present where? That page is present in that reserved area in the hard disk, right? So it could be lying in that reserved area in the hard disk. So our answer for this question is going to be what? The hard disk drive. So if a page is not in RAM right now, it is lying in that reserved area in the hard disk drive. Okay, now this question is saying that we have requested page 4, which was lying here, and we need to load it into a page frame in the RAM, but the RAM is already full, so we don't have space, which means what? An already existing page frame needs to be replaced. So we are going to, for example, overwrite an existing page frame. Let's say it was so let's say page number 2 was lying here, right? And we have moved page number 4 up, right? So we are going to do what? We are going to overwrite page number 2, and we are going to move page number 4 here. So how do we decide that we had to replace this page? Why not page number 5 which was lying here, for example. So if we had two choices, right, we could have replaced page number 5 or page number 2, but we decided to go with page number 2. And this is basically the operating system who's making the decision. Why did the operating system decide for page number 2 to be replaced and not page number 5 to be replaced? Well, the operating system has an algorithm that it follows, right? One of the algorithms, the page replacement algorithm, which decides which page should be replaced in case, you know, we don't have space in the RAM, right? Which page needs to be replaced. One of the possible algorithms is that the page that has been in the main memory for the longest time should be replaced. Okay, so now he's asking what additional data should be stored in the page table, right? Because our page replacement algorithm is going to replace the page that has been in the main memory for the longest time. We need to store information for each page. How long has that page been in the main memory? Okay, so we want to store information as additional data, which is going to tell us, you know, page number 1 has been in the memory for such and such time, page number 2 has been in the memory for such and such time. Okay, so that the operating system could take its decision. So the additional data would include the time of entry, right? The time of entry, you know, which basically means what? At what time was the page loaded into the RAM? So based on the time of entry and the present time, you know, we can do some calculation and figure out, the operating system can do some calculation and figure out that this page has been in the memory for 5 minutes, the other page has been in the memory for 3 minutes. So the time of entry, right, is going to be used to calculate how long a page has been in the RAM. So okay, next it says that page 4 is going to be loaded into the memory, but you know, when we load page 4 into the memory, we have to do a swap, which means what? Page 5 is going to be replaced, right? So we need to move page 5 out and we need to load page 4. So he's asking us what modifications are going to be made for this entry for page 4. So page 5 is going out and page 4 is coming in. And if we take a look at this page table, right, page 5 is the one that's moving out, right? Which means what? This is going to become 0, right? Because it's not going to be in the RAM anymore. And you know, this 542 is also going to become 0. But for page 4, you know, the presence flag is going to become 1 and the page frame address is going to become 542. So we are going to update the entries here. 1, 542, and remember the additional data. We are saying that the algorithm being followed is, you know, how long a page has been in the RAM. Okay, so we have to note the time of entry, right? And you can just choose any time of entry, just any random value. For example, what is the time right now? The time right now is 3:44. So I can just use 3:44 and 137 milliseconds. So I can just give any time, you know, just showing that this was the time when, you know, according to the system clock, when this page 4 was loaded into the RAM. So now using this value, you know, at any stage the operating system can calculate, you know, based on this time of entry, it can calculate how long page 4 has been in the RAM. Okay. Next he says that another possible page replacement algorithm is that we should replace a page that has been used the least number of times. So a page was there in the RAM, but you know, it wasn't used that many times, right? It was not accessed that many times, it was not read that many times, right? So give the additional data that we now need to store inside the RAM. So previously we had time of entry for additional data, but now since we have the least number of used page, right, we can say give the different additional data. This would be what? Number of times a page has been read, or we can say number of times a page has been accessed in the RAM, right? Okay. Okay, and next he says that page 3 is the page that is being loaded into the RAM, and page 1 is the page that is being moved out. Okay, so we have to fill this up, right? And let's quickly take a look at the page table. See, page 1 is going to be replaced, which means what? This 1 is going to become a 0, and this 132 is going to become a 0, indicating that this page is no longer in the RAM, right? And page 3 is going to be 1, and this is going to be what? 132, because page 3 was being loaded into the page frame that was holding page 1. So this becomes what? 132. And as far as the additional data is concerned, this is basically showing what? The number of times a page has been accessed or a page has been read, right? But we've just loaded this page into the RAM, so which means what? If a page has just been loaded into this RAM, that means that it has not been accessed even a single time so far, so this value is going to be 0. Okay, so let's fill up. The presence flag is going to be 1, the page frame address is going to be 132, and this page that we've just loaded has not even been read once so far. Okay, next he says, explain why the algorithm's longest resident and least used might not be the best choice for replacing a page. And as for the longest resident, a page that has been in the memory for the longest amount of time, it may be a page that is frequently needed. Although it has been there in the memory for a very long time, it may also be frequently needed by the process, right? So this page should not be replaced. And as far as least use is concerned, a page that has been loaded into the memory just now, that page is the least used page, and because it is the least used page, it has just been loaded into the memory, it may get replaced, although we may need to use this page frequently, right? So these are the explanations.